Hi everyone, my name is Claire Tomlin and I'm a professor of ECS at UC Berkeley. And this is Module 4 in a series of modules we're doing in linear algebra and linear systems to support the course Linear Systems 221A at Berkeley. This module concerns itself with linear maps and their properties. So we talked in an earlier module about maps and functions, maps, functions interchangeably, and some of their properties. Well, today we're going to talk about a very important property that some linear maps have of linearity that's the basis for a lot of what we do in this course, linear system theory. So we're going to start with the notation that we discussed in an earlier module, which is that of maps between now vector spaces. So suppose we had two vector spaces, and I'm going to use the sort of notation that we used last time with a vector space V over a field F and a vector space W. And W is going to be defined over the same field F. Okay, now I'm going to define a map, and I'm going to use this notation script A to represent the map, or a map which takes elements of V to elements of W. So it's a map or a function. A is said to be a linear map if the following property holds. So A is linear if and only if the following property holds. That's if you take A and you operate on a linear combination of elements in V, alpha 1 V1 plus alpha 2 V2, then a property called superposition holds. This equates to alpha 1 A of V1 plus alpha 2 A of V2. And this is true for all alpha 1, alpha 2 in the field F, and for all V1, V2 in the vector space V. Okay, so this is our map notation. A operates on elements of this space and gives us this linear combination of elements in the space W. So here A of V1 and A of V2 are elements over in W, where V1 and V2 are elements over in V, our domain and codomain respectively. Okay, so this is a very straightforward, simple property. It's called as superposition. Let's write that down. Superposition. And it's typically easy to state and it's easy to check. So we can do a number of examples. Let's start with an example here. So suppose you were given a map A, and we're going to define it as follows. It takes elements which are polynomials, as squared plus bs plus c, and it maps it to polynomials. And all I've done is I've switched the first and the last element here. So cs squared plus bs plus a. And the question is this a linear map? So is it linear? The answer is yes, but in order to support the fact that it's linear, what one would have to do is show that this property holds. Okay, so let's quickly go through that and show that the property of superposition holds for the map A, which is defined in terms of what it does to elements of this space of polynomials. Okay, so the way to do this properly is to just show this holds. So we're going to take two elements of our space, V1 and V2, and I'll just write them as follows. V1 is A1s squared plus B1s plus C1. V2 will be A2s squared plus B2s plus C2. And now I need to show that A of alpha 1 V1 plus alpha 2 V2 is equal to the linear combination alpha 1 A of V1 plus alpha 2 A of V2. Okay, so now this becomes just, it just becomes algebra. We plug in the V1 and V2, and then we use the definition of A to calculate what A operating on this linear combination of V1 and V2 is. Okay, so we can just write that out. That's A of, so this is going to be alpha 1 A1s squared plus alpha 1 B1s plus alpha 1 C1 plus alpha 2 A2s squared plus alpha 2 B2s plus alpha 2 C2. And now I can rearrange the I can rearrange the coefficients of the polynomials. So this is A operating on alpha 1 A1 plus alpha 2 A2s squared plus alpha 1 B1 plus alpha 2 B2s plus alpha 1 C1 plus alpha 2 C2. And now I apply my map. So I take that element and I apply the rule of my map, which is just to switch the first and last coefficient of that polynomial. And so what I end up with is alpha 1 C1 plus alpha 2 C2 S, so I don't need that outside bracket, S squared plus the middle coefficient stays the same, alpha 1 B1 plus alpha 2 B2 S plus alpha 1 A1 plus alpha 2 A2. Okay, and now you can see all I have to do now is rearrange the coefficients and bring out the alphas and show that that is indeed equal to alpha 1 A of V1 plus alpha 2 A of V2. Okay, so those last few steps you can show yourself. Okay, so that's a simple example. We can do another couple of examples. So here's the example we just did. Suppose I took that same polynomial and now I redefined A to be the following. A takes that polynomial and it's going to give me the following function, which is an integral. And so we can ask, is this linear? Now we have a procedure to show it's linear. We just have to do the same thing. Take two elements of V1 and V2 from my domain. So I would choose the same elements, V1 and V2, as I had in the previous problem, and then perform the map A. So operate using this integral instead of the previous. And so you can go through and indeed show that that's a linear map as well. How about the following? Here's another example. So yes, that was linear. This third example, A is going to now take functions of time, V of t. Okay, so my domain is a space of functions, and it takes them, and so it takes that element V of t, and it gives me the following. It integrates V of t between 0 and 1 over time, and it adds a constant to it. And we ask, is this linear? Okay, so we perform the same test. So the rule, if we're not sure, we always just go back to the same test. We choose two elements in any two elements from our domain, and we look at the linear combination and ask, under this map, as defined here, what does that map to, and can I rearrange it to be of this form? Here, if you do that, you'll find that for a general constant k, this map is not linear. If k is equal to 0, it is linear. But if k is some non-zero constant, this map is not linear. It's actually what one would call affine. One more example. So this is not linear. And let's do one more example, just because it precedes something that we're going to be doing in a minute. Suppose we look at a map A, which takes it takes vectors in R3 and it gives us vectors in R3. And the operation A is just pre-multiplication of a vector by a 3x3 matrix. So A of V is actually defined as a matrix A times the element V. So again, this is our operator notation, and this is matrix multiplication, where A is a 3x3 matrix. So I'm going to write that as R 3x3. And so the question is that a linear map? And it's fairly easy using this same principle of superposition to show that indeed that is a linear map as well. So that's the definition of linearity and some examples. And to conclude this module, we're going to introduce two concepts for linear maps that we've seen in the definition of functions previously. So we're going to define the range space and the null space of a linear map. And we've seen these before when we talked about functions. And we're going to show something about them. Okay, so suppose we have a linear map A. Let's go from a space U to a space V. And so A is linear. We define the range space of A, range space of A, or R of A, to be those vectors in our codomain V such that V is equal to A of U. And that's for all U in our domain. Okay, so they're basically elements in the codomain that have come from elements over in the domain. So we've seen this definition before. And we define the null space, or N of A, to be those elements U of the domain which map to the zero vector in V. So they're elements U such that A operating on U is equal to the zero vector, and that's the zero vector in V. We often call this the image, the range space, the image of A, and we often call the null space the kernel of A. Okay, and there's two important theorems that are very easy to prove. We can prove that the range space of A is a subspace of the codomain. And we can prove that the null space of A is a subspace of the domain. Okay, remember our definition of subspace from a previous module as being a subset of the corresponding space, which itself is closed under vector addition and scalar multiplication as defined in the parent space. So I won't prove these in the module because they're very easy to prove, and you should do that as an exercise. And finally, we can state one more theorem, which I'm also going to leave as an exercise, which is that if you look at the range space and null space of linear operators, then they have two very important properties. Okay, so we're going to consider the same structure. A is a linear map from the space U to the space V. And I'm going to consider a vector B, which is in my space V. Okay, so it's just a general vector in V. Then the following must hold. If we look at the equation, A operating on U is equal to B. Okay, so again, U is an element of our domain. A is a linear operator. And that A of U maps over to B in the codomain. So this is what we call a linear equation if A is linear. Okay, so this has at least one solution. It has at least one solution. What that means is that linear equation has a valid solution U in the domain, meaning that there is a value of U which makes this equation hold. Okay, so that statement that it has one solution is equivalent to saying simply that B must be in the range of A. Okay, so what that's really saying is that B in the range of A is the least we need for that equation to have a solution. We don't need that A is invertible. We don't need anything more than just B is in the range of A. Now, if B is in the range of A, so if B is in the range of A, then we can say two more things. We can say, first of all, and I'll write it down here at the bottom of the board, that the linear equation AU is equal to B has a unique solution, if and only if the null space of A is simply the zero vector. So we write that as the zero vector in U, and because it's a set, we'll put curly brackets around it. So what this means is that the only thing in the null space is the zero vector. If that's true, then this linear equation has a unique solution given that B is in the range of A, and vice versa. So this is a very strong property, and it's very important. And finally, one last thing about that. So we'll write the second part of that theorem up here. That if we're given a particular solution, so this is the second part of that, of this theorem. So suppose we had a vector x naught, and that's in the domain U, such that A operating on x naught is equal to B. Then if AU is equal to B, that must imply that U minus x naught is in the null space of A. Okay, so in these two statements here, we can relate the null space and something about the size of the null space to the solution space, the null space of A, to the solution space of this linear equation. Okay, so that concludes our module on linear maps, and we will continue next time with a discussion of using this definition of linear maps to come up with interesting properties of functions.